Hi, everyone. Thank you for joining another session of the ZK month with TPG. We have Sneha and Laisha today talking about how to build full stack ZK dApps. Sneha and Laisha, please feel free to introduce yourself and we can start off with the session.
Sure. Thanks, Nivedita. I'll go
I've
first.
given both of you access. Can you just check?
To share my screen?
Yeah, to share.
Yeah, I see the option to do that.
Okay.
Perfect. Hello, everyone. My name is Laisha, and currently I'm heading developer relations at Pesto, but I come from a developer background. I've been at Goldman Sachs. I've built a lot of Web3 dApps. I've built my own product in Web3. So today I'll be talking a lot about ZK, and I'm sure all of you are excited to kind of get your hands dirty with code. Over to you, Sneha.
Okay, hello everyone. My name is Sneha. I am a smart contract developer, currently working in a Web2 company, switching jobs very fast. And I am also a technical content writer, and like I take sessions on behalf of TPG, being one of the directors for TPG Delhi. So yeah, that's it. We will get started with the session. It's going to be a long one with a lot of jargon terms and a lot of mind-boggling things. Laisha and we are well aware. We needed a lot of time to prepare for this 2-hour session. So just be patient, and whatever doubts you have, you can, ask it right away.
Yeah, if anyone has doubts, they'll either, I guess you can just put it on the chat or you can raise a hand and one of you can, take it up.
So I'll share my screen. Okay, is it visible?
Not, yeah, it is now.
So today's session is going to be about a zero knowledge dApp from zero to production. Too many zeros in the title. I hope that is not the percentage of knowledge that you take from here. A joke that I was trying to land on. Really nice. I don't know how well it worked.
I have laughed.
Okay, so the introduction is anyway done. So this is how the session would look like. We will talk about the objectives going forward to the workflow of the project. You guys might be well aware of what ZK is, but we will do like a very quick recap, 1 or 2 lines. We'll talk about components of ZK. Then we will discuss what are circuits and circom, because these two terms are going to like pop up very often during the session. Then we'll talk about snark.js, and then we'll be moving on to code. Okay. So the objective of the session is to explain the flow of a ZK dApp. Like if you're trying to build a zero knowledge dApp, how should the thinking process be like? And we'll try to code it from scratch and then make it production ready. For today's session, we will be creating a ZK dApp to prove that someone knows how to solve a Sudoku game without revealing the answer. Pretty obvious, because when we're talking about zero knowledge, we are trying to prove something without actually revealing the right information about it, and just pointing out hints towards it so that the other person is able to understand it well. We will be using Circum for writing circuits, Solidity as the language for writing smart contracts, and JavaScript for the front-end segment. Okay, so this part is very important, because in order to get started with any project, not just this one, it is very important how we proceed with the workflow. Looking at the backend side of it, we will start with the creation of circuit. The folder segment of this project looks very complicated. It's like too many files under too many folders. So we have to be very careful with that one. So we create the circuit, we compile the circuit. There are certain input files that is needed to be put in. Then we will be generating the witness. We test the circuit, and then we create, test, and deploy smart contracts. you might not be aware of, what witness is here in this case, if you are well and good, but we'll be talking about this in the coming slides. For the front end segment, it goes on very simple. We create the next.js application, we add the necessary libraries and dependencies, we add zero knowledge to the front end, then connect the front end part with the smart contracts. We add all the utility files and whatever files that are necessary, and then we finally deploy the project. Okay, cool. So talking about what is zero knowledge, anybody who would want to answer this, even if the answer is on the screen? I mean, whatever your understanding of zero knowledge is. Okay, nobody. Fine. So as you can see, zero knowledge proof is a way of proving the validity of a statement without revealing the statement itself. Now that can go for like a lot of things. If I have to tell someone that I am 23 years of age or so, instead of revealing that information, I might just point out or give you, equations, or just point out anything that would, give you a hint that the answer is around 23 or so. So the whole idea is two party being involved, one party being the prover, the other party being the verifier. So the prover is the party that is trying to prove a claim here, while the verifier is responsible for validating the claim. So it can be like me and Laisha are talking, and I have to, tell her, I have to prove her that I'm 23 years of age. So in this case, I am the prover who's trying to prove a claim that is my age, while Laisha would be the verifier who is trying to validate, that whatever I'm saying is right. So if you look at the whole structure when we're talking about zero knowledge proof, there are three elements that we talk about here. One is the witness, the other is the challenge, and the third is the response. Okay, so witness, whatever we are trying to prove here when we're talking about the zero knowledge proofs, that is whatever knowledge that the prover is trying to prove, right? It is some hidden information, and whatever information that is the witness to the proof. If you read this line in the first go, okay. Did I do these red lines here? Anyway, yeah, so what I was saying was, whatever, suppose if I am trying to prove Laisha that my age is 23, whatever proves, whatever equations, whatever scenarios I'm trying to give it to her, that is based on the secret information that my age is 23, right? So the witness in this case is the existence of my age being 23. Okay, and whatever the prover is, like whatever knowledge that the prover has about the witness will help the prover set up or establish a set of questions that can be, answered by the other party with whatever information, knowledge that they have. So if I know that the answer or whatever age number that I'm talking about, that is 23, I will always try to give out equations that will land in and around 23. And that is what Laisha has to figure out, right? So I have a witness and I am establishing a set of questions on basis of that particular witness for the other party to answer or figure out that whatever I'm claiming is correct, right? The second component goes as the challenge, where the verifier will randomly pick another question from the set and ask the prover to answer it. Whatever claims that I'm trying to make, the verifier will, ask more questions and see every time if the answer is around the claim that I'm trying to make, right? And third element is the response, where the prover will accept the question, that will calculate the answer and then return it to the verifier. And so the response segment becomes very simple, that whatever questions are coming up and whatever answers you're calculating, you're returning it to the verifier for him or her to, accept the claims that you have. Cool. The other thing that I would like to discuss here is about non-interactive zero knowledge proofs. Throughout what we have discussed here, it shows, it's very evident that the whole conversation between the prover and verifier is happening quite rapid. So there's one claim, there's another set of questions, there's a response to it, and the cycle continues. But when we're talking about something as non-interactive zero knowledge proofs, they are like a particular type of zero knowledge proofs in which the prover can generate the proof without any interaction with the verifier. Now, how exactly is that being done? They're making use of smart contracts. Okay, so they will allow smart contracts to act as a verifier so that anyone can generate a proof and send it as a part of a transaction to the smart contract. And whatever actions that you have to do, depending whether the proof is valid or not, will be performed by the smart contract on its own. Okay. And when we talk about non-interactive zero knowledge proofs, the first and the most preferable are ZK snarks, okay, which stands for zero knowledge second non-interactive argument of knowledge. So the terms are pretty clear, particularly stressing on, the definition. The word succinct here very clearly specifies that whatever it is, it's like simple and clear way of saying things. If you talk about the dictionary meaning of it, so you are clear in whatever you're claiming, but there's no interaction happening between the prover and the verifier here. Okay. Cool. Okay, so third thing that I would like to talk about would be circuits and circum. Okay, so these two are like the backbone of the code that we are going to do today. Talking about circuits first. Arithmetic circuits are mostly used as standard models for studying the complexity of computations. Okay, so just like we're writing smart contracts in a particular DApp that we're trying to create, when we're writing ZK Dapps, apart from writing smart contracts, we're also writing circuits, right? And if you get into the mathematics of it, it is it is kind of complicated in terms of the other elements of it. But to simplify it and understand it in a manner, you can just understand it as that it has like addition and multiplication gates, and it will have like values that are elements of a prime finite field FP, where P actually is a very large prime number. Okay, so I don't know how many of you have done programming for microprocessors. There also we had to kind of write circuits, and the programs would all be dependent on the registers and other elements. So here also we're talking about gates and we're talking about signals. The prime number that we are working on is very huge. So that is why I've particularly added a disclaimer here that if a given prime number P, the finite field that we're talking about mathematically has to be a set of numbers that starts from 0 and goes to P minus 1, on which we can add and multiply these numbers with modulo P. Okay. So you will see the use case of it, and there are certain reading materials that we can provide by the end of the session for you to refer, and the research papers if you want to get into the mathematical side of it. Talking about circoms, circom is a domain specific language that we particularly use to, write arithmetic circuits. And it has an associated compiler of arithmetic circuits that give out respective rank 1 constraint system. Okay, so I know that this does not like sound very understandable, but once we explain you how the flow of the inputs and outputs are working for the project, you will be able to understand what exactly are we trying to talk here. Right now, all you need to understand is that we are working on circuits, and in order to write circuits, we're using a language circom. And particularly for zero knowledge circuits, we make heavy use of circom. Initially it was written with JavaScript, but I think that is depreciated, and now like it's mostly written in Rust. The other thing that we have to keep in mind is the snark.js. We will be very importantly using snark.js, which is an NPM package that contains code to generate and validate the ZK proofs from the artifacts that we have, got by circoms. So it's like a huge set of inputs and outputs that we are talking about. Moving on to the next slide. Just a moment. Yeah, okay. So you can see this, right? So the definition when I was talking about circuits being, taking some prime number and doing the addition and multiplication gates and operation, this is how a particular operation would be shown. So there are, whatever we are taking at as inputs here goes as input signals. So instead of just inputs, when we're talking about circuit and in their lingo terms, we talk about input signals and output signals and intermediate signals and so on. So here we have got 5 signals. Here we perform the multiplication between A and B. What we get here is the intermediate signal, and then addition is performed on the input signal C and whatever product that we have got here, and the rest output is what we store in the output signal. Okay. If you look at the structure of the circom program, you will see that there is like a witness generator, there is constraint. These constraint takes you to the rank 1 constraint system, which is then provided to snark.js that we talked about right now. This is exactly what was written in the previous slide, that it's a NPM package that takes whatever attribute was generated by circom to validate to the prover and verifier in a zero knowledge program. Okay. This is another structure that will kind of give you an idea that how the circom witness, the snark proof and everything is working. Whatever we are getting from the Stark recursion component, whatever we are inputting into the Stark recursion component, once that is processed, the output here is a Stark proof, and this Stark proof goes to the circom as input. Okay. All of you might be aware that the ZK prover is a state machine, but it is kind of emulating EVM in general. And the whole process of generating a witness for the file, they're using a tool that is based on arithmetic circuits written in a circom language, right? So then when you are putting it as input, witness is generated, then it is put into rapid snark, and then we get the snark proof in the end. This structure is again similar to what we were talking about circom and snark.js in general, that whenever we are designing our arithmetic circuit and writing it using circom, there are two potential options. You can use your own code or you can use safe templates. Now, all the pre-existing templates is provided in circom library, which we will be further using in our project. so that, we reduce our manual task, and whatever can be done through libraries can be easily done. The second part goes as compiling the circuit and get a low-level representation of it. That is the rank 1 constraint system here. Then we will use a snark.js to compute the witness, because what we are getting is output from the circom is a witness, and we'll be using snark.js to compute it. These are the respective commands. Then we generate a very trusted setup and get a snark proof. And just like in the previous slide, we saw that this snark.js gives you respective prover and verifier proofs. So that is what we are trying to do here. We are doing a setup and then getting ZK snark proof, and then validating our proof or have a smart contract to validate it whatever way we want. For this project, we will be writing smart contracts to, verify whether a person knows how to solve a Sudoku or not. And the whole structure goes on to giving input signals, that is unsolved Sudoku, and then having solved as the answer, so that we can do like a quick comparison, have an idea, and then write respective smart contracts to it, and then deploy it to front end. That is all that we had for theory, to just give you a quick overview. And now we'll be proceeding with the code, and then as we proceed with the code, we will keep explaining you, what this particular file does and how is the thinking process associated with it. So, Laisha, I think you can take it.
All right. Thanks, Neha. I think now ZK becomes a tad bit more simpler for us to understand. Too many terms, but I think now we get how it functions, what are the components. So what we'll be doing now is two things. We'll first start with a very, very simple example to understand how to write a very, very basic circuit, because you cannot, it's not very easy to translate very complex logic into these circuits, because what we are talking about is nothing but a mathematical equation, right? Where we have few things which we cannot expose. There are few things which we can, right? The output will always be known. There will be some elements of that equation which can be exposed, but the private part of it is something that we don't want people to know. So we'll start with an example and understand how to go about writing a very simple multiplication equation in terms of a circuit, and then we'll start with building our ZK Dapp. If you want, you can do a hands-on with me, though I would suggest that it will be a little fast-paced, so you might miss out on a few things. Let me just start sharing my screen, and then we can go ahead. Just give me 1 minute. Okay. Just give me 1 minute. I'll have to drop and join back because of some sharing settings on my Zoom. So just give me 1 minute to join back in.
Yeah.
All right. Thank you for the patience. And I hope all of you can see my screen.
Yes. You can
Okay.
see it.
So I don't want to delve too much on theory, but I feel some concepts need a little bit of a deep dive, because that's when you will be able to write the code properly and also understand, right, what is happening. So by now, one thing is very clear, that we are going ahead with using Snug.js, right? Now, what is it enabling us to do, right? We know that there's a witness that we need. We also know that there's an equation that we need to build, and whatever elements that are participating in that equation, those are called signals, and there are constraints. So a snark is basically allowing us to prove that whoever is basically generating the proof, that I know a set of signals that is matching all the constraints of my circuit, which means that I'm able to satisfy all the requirements of a circuit without revealing any of my signals. Now, that's a lot of jargon, but let's understand with an example. So let's say I'm just trying to do A into B plus C as an operation, and I'm giving an output. In this operation, D will obviously be an intermediate output that I'll get. So essentially, there are 5 total signals, which is A, B, C, D, and my output, right? Where let's assume that maybe A is a private key, B is another, like a part of public key, C is also a part of public key, and together A into B plus C together makes out, like it is able to verify that they are the right combination. And obviously B, C, and out is something which people can know. Now, what we need to do is we need to come up with some sort of mathematical operation which lets us generate an equation where we are able to generate such constraints, where we don't need to reveal A, but with the presence of B, C, and output, we can build such, I would say, scenarios where we can say that if A was like this and B and C, our output are like this, we can reach to that output without having to reveal A. So let's understand that when we are doing our building of the DApp, what are the things that we are going to use? And before we go into the nitty-gritties of it, we will be focusing a little bit on Circom and Snark before we start coding. So we'll use npm yarn for all of our dependency management. Circom is something that we are going to use for building, like testing of our circuits, generating our circuits, compiling it. Snark.js is basically for the verification of our proof and using that proof further and interaction of our smart contracts. Those are the major things that we want to do. Now, let's look at a very, very simple circuit. All of us understand that circuit is nothing but translating whatever logic that we want to implement into some sort of a mathematical equation. Now, let's say my equation is A into B plus C equals to something, where let's say C in this case is 0 because it's just a simple multiplication. So I have 2 input signals. One is A, one is B. So this is something which goes without saying. We're basically defining the version with which we want to run it. We have defined our template phase, which is, you can call it pretty much anything. So generally, the first thing that we start with is the declaration of our signals. In this case, we have 2 inputs and we have 1 output. Your number of inputs can change. It can be any number of inputs. And what we want to do is A into B. This can either be less than equal to or greater than equal to for this particular example. Now, I have generated this circuit. What do I do next? How do I get the proof? How do I go with generating my witnesses? What are the steps that are involved? So let's look at it at a very simple example so that we are able to understand it when we are doing it on a very complex example. So now that we have our circuit, right, it's a high level language. Now we need to compile this circuit so that we are able to represent it in the form of, you could say, in a simpler format, which in this case will be R1CS. We'll look at what R1CS is and how we are going there. So what we are basically doing is whatever circuit we have written, in this case, it's multiplier2.circom, we are asking circom to compile it, convert it to this representation of both R1CS and WASM. So WASM is basically WebAssembly. WebAssembly basically helps your compiler to understand what to do on top of it. Circom is nothing but a Rust compiler, which is able to understand the arithmetic operations that we have written in our circuit. Now, let's say that we have done the compilation. what are we going to get? And let's also understand what are these three things doing for us, right? So what we are doing is we want to have certain constraints for our equation. We want some witnesses. We also want a compiled version of this circuit to do anything further than this. So this particular argument is responsible for generating that constraint system, right? So I'm sure many of you would have studied the optimizations or linear optimizations and non-linear optimization in mathematics. It's something along those lines, not entirely. There are constraints involved, there's an output involved. In our mathematics, we used to deal with very simple constraints, and our output used to be either maximization or minimization of a certain value given the constraints. Here, the constraint system is such that we want to come to the solution without revealing certain parts of our inputs, right? So let's say we have got a particular representation. The second thing is we also need a WebAssembly code. Now, what this is, it is basically used together with our constraint system to generate the necessary witness, which will act as input for us to generate and verify our proof. Now, that aspect is handled by Snark, but all of the inputs that are needed by my Snark is actually generated by compiling of my circuit. Then this is an argument which is basically a symbols file which is required for debugging. So I mean, it's good to have it. And then there are also there are multiple ways of going forward from here. You can either use the WASM and R1CS representation to generate your proofs. You can also use CPP files to generate it. So it's good to generate both depending on the kind of system and stack you're using. You can use the input of your choice. In this example that we are building a DApp, we'll go ahead with R1CS and WASM. But -C is basically to generate all the compilations and all the binaries in terms of CPP file. And basically, if you want to generate witnesses using C code, you can also go ahead and do that with Circom. Now, you know what is a witness, but just to reiterate on that, right? Before you create the proof using Snark, we also need to calculate all of the signals of the circuit that are matching all the constraints of the circuit. It isn't at least one, it has to be all of them. So what we are doing is we need to provide a file with all of the inputs, and the module will basically execute our circuit. It will calculate all the intermediate signals. I mean, we saw the examples, right? A into B, the intermediate signal was D there. And it'll also calculate the output, use that. And the set of inputs, intermediate signals, and the output, these are called witnesses, because they are the ones who are, you could say, it's a circuit satisfiability that they are adhering to. That is what witnesses do, and that's their job. So in our case, we want to prove that, let's say, number 33. So we can assign 3 and 11. We could also take 1, A is equal to 1, and B can be 33, right? So there are multiple such combinations that are possible. So let's say we were able to generate all of them that were able to satisfy this constraint. Now comes the important part, which is proving my circuits. So I have compiled my circuit. I've also run the witness calculator with all of the appropriate inputs that I have. Now what we'll have is a witness file that contains all of the computed signal. We'll also have an R1CS file, which is the initial constraint file that we had generated describing the circuit. Now, these are the two important inputs that will help us generate our proof. So what we are going to do is simply use Snark.js to prove that we are able to provide basically these two factors for the number 33, right? We won't be revealing what A and B is, but we know that we are able to come to 33 in whichever way we can. So a lot of you would be thinking, how do we decide how the proof will be taken? What proof will be taken? Is there a protocol around it? So in general, around Snarks, there are two protocols. There's Groth16, there's also Plonk. Both of them are used in specific use cases. You will see some of them using Groth16, some of them using Plonk. The choice comes more at a level when you are looking at the size of the proof that's being generated and the speed at a very granular level. So for the simplicity of things, I've started with Groth 16, but you'll also get resources to do this entire dApp building with Plonk. So for now, let's understand a little bit about Groth 16. So what we are doing is we are using a trusted setup, which means that my prover and my verifier are not going to interact with each other, right? So which we mean that we can trust that the prover is not going to rely on any malpractices, and so does the verifier. So in case of Groth 16, you require a trusted setup per circuit, which means that any interaction that will happen like for every interaction, you'll either need another verifier that will do it, or you will have a smart contract do that aspect for you. So there are two important parts of this trusted setup. The first is powers of tau, which is irrespective of the circuit. It has to be there. The phase 2, which is again some sort of mathematics, it actually depends on the circuits that you have. So the main idea behind powers of tau is that, we want to introduce more randomness into the system, because if it's too simple, it's too easy, or rather I would say it's like it would take lesser time for any individual or a group of machines to tamper with them or compromise it, right? You can back propagate and come back to the entire place where we started with. So the idea behind powers of tau is to introduce some randomness into the system. I'll show you some ways in which it is done. The phase 2 basically depends primarily on the circuit. Let me show you one simple example of how this is done. I hope you can see this particular tab. Yeah, okay. So what exactly happens is that we first have to start a new powers of tau ceremony. This is nothing but it's something that is handled by Snark.js, but it's like introducing some randomness into the system through a bunch of seed phrases. And then we contribute to the ceremony, which is basically telling that this is how we are starting with the randomness. The phase 2, as I mentioned, is actually circuit specific. Depending upon what you are doing, you will go ahead with that. But generally, you can use the default phase, which is provided by Snark.js. So why we are doing this is because we need a key file, right? Which will be necessary for the verification aspect. So this is the first thing that we do. We generate our key file. And then using this key file, we say that we've contributed to the phase 2 also. So we export this verification key so that we can use this in our further step. Now, let's say everything worked out for us and I've been able to generate my key, which I am able to use for verification. Then what I need to do is I need to build a proof that I'm going to use as part of my smart contracts so that I can use that as a signal for going ahead and doing any operations, because smart contracts are automated. So whatever signal they are going to get, you are going to either trigger some sort of function or you're going to execute a transaction. Now, I would also say that snarks are very I would say suitable for a trust-based system, because you can rely on a smart contract to do the, I would say, calling of the functions based on the ZK proof, because you don't have any interaction between the two. And then another thing that also makes it important is because since there is no interaction, right? So anything that will happen can happen through a transaction, and you will have to send the call data, whichever would have come from your ZK proof. So whatever verification key we have here will have to be sent as part of your call data so that the system knows what was actually happening. And once you are generating a proof, right, you have your key, you have your witnesses, you have whatever is the expected output. You basically get two files, which is the proof.json, which is your proof. And this is the public.json, which contains whatever public aspects you have. In this case, we only had the outputs. And similar to how we were proving it, we can also verify our proof using the verification key and these two values, these two files which we generated. Now, all of this sounds very simple from the aspect of a very simple problem of multiplication. But in case of real world scenarios, it's a little bit more involved. Also, if you were to do this verification from a smart contract, things will get a little bit more complex. So let's get started with the code and let's understand how to go about it. Let me share my screen and get started. So how we'll go about this is I'll walk you through a little bit on the code structure, and then I'll show you what each one of them does by going module by module. So we'll start by creating our circuits. Then we'll go to the contracts, and towards the end of this session, we'll do the UI aspect of it. Okay, I hope you can see my terminal. Let me know if this text is too small to read. I can increase.
Yeah, can you increase it a little bit more?
Is this better?
Yeah, I think this is good.
Okay, perfect. So, okay. So let me show you the code structure a little bit. So as any, like in terms of building a DApp, what we are very familiar with is we have certain contracts and we have a UI to interact. Like we have certain JavaScript clients that we build so that we can interact with our blockchain backend. And then we have some UI wrapper to basically have a rendered UI for interaction. Now, what we are adding here is the circuits, which means that whatever components that are interacting or whatever actions that are being taken in my smart contract, I'm not revealing the data on the basis of which I'm taking. And for today's DApp, we are taking a Sudoku example, which means that we are building a ZK Dapp where you will solve the Sudoku without revealing the solution of the Sudoku. So naturally, the first thing that we need to do is basically build a circuit that understands when is a Sudoku considered complete and how to handle it. So we'll get started with that. So let me walk you through of how we'll go about it.
Laisha, there's a question.
Yeah. Let me check. Most of the circum programs I have seen usually work with numbers. Is it possible to write a circum circuit to prove that someone has the private key that was used to sign a transaction? Yes. There are protocols that are trying to make it simpler for you to do this instead of you writing it from scratch. See, with a private key, it gets a little bit more complicated because you have to abstract your private key in a way that, one way is you take it off chain, generate some sort of hash out of it, and then use that as part of your program. That is what we used to do without ZK. When you're talking about ZK, you have to come up again, you have to make your equation or constraints difficult enough that people are not able to understand it's a private key that you are dealing with. So once you look at this Sudoku example, right, you will be able to understand what is happening. Also, for the like with the given the paucity of time, right, we won't be delving at every line of code here because it will take us too long to complete this session. But what we'll be doing is we'll be understanding how to stitch together everything, what each step is giving me, and how I can use the different components that a ZK proof generates and use it in my existing DApp logic, because that is what is most developers struggle with, right? When you're talking about applications that you've built, it's very difficult when you have to formalize a circuit around it and use that in your existing DApp. Like, it's about introduction of a ZK component in your existing DApp, how you can go about it, and how you can wrap everything together into a good UI, which you can use. So to answer your question, yes, that exists. I will probably get someone to send you some resources on how it's like currently it's a research problem that I've mostly seen, but I know of a protocol that is trying to solve for it. So I'll send some resources through the community channels. I hope that answers your question. Okay, so what we are going to start with is we've started with a very like you can call it anything. I'm just calling it ZK Sudoku. And the first thing that I want is to basically have a circuits directory. As part of this circuits directory, I'm going to have all of the ZK pros, ZK aspects part of my circuits directory. So the first thing I'm going to do is I have to basically initialize a yarn package so that I can have all my dependency here. So I'm just showing it to you for the circuits aspect. We won't be doing all of this for the contracts because contracts are a little bit more intuitive. For the precursor, we will be basically like for you to get started on this, you need to have all of these dependencies. You will get resources of how to install all of these. Most of these can be installed through NPM packages. Circom, you'll have to go through a distribution that they provide. So you can actually install it through their Git repo, or you can like mostly it's Git repo, and then you have to just build this so that it's available in your system. And the installation is pretty simple. So, I mean, you can do that at your convenience. Now, what I need to do is I need to have circumlib library. Now, circumlib library has certain templates of circuits. Now, it's very difficult to always write a circuit from scratch. So what I'm going to do is I'm going to add this dependency as part of my yarn package. Okay. So to show you, basically, I've just added the circumlib dependency for now. Now, what I'm going to do is, since we are dealing with Sudoku, right, I'm going to make another directory called Sudoku. And I'm going to start writing some circuits as part of it. Now, what I want to do is, I have, like, how many of you have played Sudoku here? Maybe I can get a raise of hands, maybe. I mean, I'm assuming some of you have, for all the people that are here. Okay, very interesting. Let me show you what a Sudoku looks like. Okay, so Sudoku is basically a mathematical game where there's every square, a 3x3 square that you have, there are 9 numbers that are there in each square. And then you have to make sure that in any square, in any line horizontally or vertically, each number has to appear only once. And you basically start with a set of numbers that have been given. Depending upon the level of difficulty, it can be less or more numbers. And the goal is to solve for this. Now, what we're trying to do is, without revealing everything of how we solved it, we want to prove that we've actually solved the Sudoku, right? So we basically need to first start with building a circuit around the logic of our Sudoku. So let me walk you through the circuit a little bit. Okay, so we have an unsolved Sudoku and we have a solved Sudoku. So what we have to check for is that the numbers should be between 1 and 9. And each number in the solved Sudoku is to basically check the horizontal, vertical, and in a grid, like the 3x3 grid that we have. So we are basically running 2 for loops to check for those 2 constraints. Another thing that we have to check for is that whether if I'm able to go from unsolved to solved, right? Like I have to check the feasibility of it. So this is what this entire code is basically doing. So I have to, one simple way of doing it is you can do the matching of number by number by running 2 loops and handling all of the edge cases that none of the elements are actually, like there's no repetition of the elements. All of the elements are falling between 1 and 9. And for each of the element that is actually solved, which is there in the solved, it should always be same as in the unsolved part also. And this is where we are actually doing that. Just as a question to all of you, if you were to check that if a person has solved the Sudoku correctly, how would you go about it? Given that your Sudoku looks probably something like this. Let's say this is a Sudoku they started with, and you have another Sudoku to compare it with, right? How would you go about it? Can anybody probably try to like give it a shot? You can be wrong, that's all right, but try to give it a shot to understand what's happening, so that it, to build upon the ideology of what's happening, it's important to understand what Sudoku is.
Can I speak?
Yeah, go ahead.
Okay. On my own, I'll say that I'll go through all the rows and all the columns and make sure that like no number is repeated. And I'll also make sure that the person did not change the initial numbers that were in the rows and columns. I think that's how I'll go about verifying that.
Yeah, exactly. So essentially, one way is you build another structure, right? Where you basically mark, like you compare if whatever element that you were expecting to have, if that same element is occurring, you can mark it as 1, otherwise you mark it as 0. That's another way to easily handle it by like building another dynamic structure which is of size 9 cross 9. So that is also another way of doing it. So what I'm trying to tell you here is that if you look at this particular input, right, these are both of my inputs, in which my unsolved is the public input signal, which is aware, which is what I'm trying to solve for. So it is the unsolved Sudoku component, right? And solved is a structure that I'm using to basically check and see if all of the elements are as expected or not. Now, if you look at it as part of this circuit, this is one interface that I have built, or you could say a template phase, as we call it in circuits, that is present. Now, let's for now assume that this logic works for us, right? Delving into this logic will probably take me 45 minutes or more to walk through. So let's for now assume that by having another auxiliary data structure which marks it as 0 if the element is not matching and 1 if the element is equal. And it's nothing but dynamic programming principle that we are working on. So we basically create a main component and initialize an object of that particular template phase. Now, why we do that is because we want to generate the component representation and witnesses after it. So that's why we are going ahead with that. Now, the next thing that we want to do is, let me just create this right now so that we basically see what are the different components that are generated. So what I'm going to do now is, like, this is the high level circuit that I have. Now I want to go from the high level representation to the R1CS representation that I have. And I also want to generate my WebAssembly file. So let's go ahead and compile the circuit. Now what compilation will do is, it's going to generate these files. So for the ease of doing the compilation, let's just write a compile file so that we can use the script to compile all the circuits that we'll write. Okay, so I've written a generic script. You can choose to basically compile your circuits by running this command every time, right? So what basically I've done is I'll pass a command, like whatever circuit I want to build, as a command line argument to my shell script so that it compiles that circuit which is present in that directory. All right, so let's see what happens once I generate this particular, once I compile my circuit. So let me create this file here for you. Why I'm doing this is because all of this is already generated. So I want to show you what all gets generated after I create it. So I need to basically give it the right permission so that I'm able to use it to execute. So I'll just give it execution permissions. And now let's go and run it. So if you look at it, it has generated my R1CS representation. We've got our WebAssembly file also, and we've got all of these like system file is this is a symbols file which we don't need because all of the like everything went okay. So we don't have any debugging to do here. And this is all CPP files which you can use if you want to use a C program to generate a proof. Given that we are using Snark.js, we are good to go with R1CS and WASP. Now, what we have here is good. Now, if you remember, we need an input file which will act as our signals to be able to send it to the witness generation aspect, right? Now let's go ahead and generate an input file. I've already pre-written that input file, so let me show you it. Now, input file is looking something like this, where all of the, like if you see these elements, these are the ones which were already present. And solved is the one where all of the correct elements are there. Now 0 here represents, which means no number was present. 0 is the place which we have to solve for. Solved is the correct solution. So this is one pair. You can give more than one. I mean, it's a dictionary, so you can give as many inputs as you want. For the keeping in mind the size of the proof that we want to generate, I have started with 1. So now that we have this, what we need to do is we need to generate witnesses. So let me go ahead and build an input file for me. Now, in order to generate the witnesses, what we have to basically do is call the generate witness.js file, which pre-exists. And what I'm going to use as inputs for that is my R1CS representation. I'm also going to use my WebAssembly, and I'm also going to use my input JSON. And what I'm expecting as output is nothing but the witness file. And as a sanity check, it's good to always compile your circuit and then generate your witnesses. Given that we have compiled before, we can also skip this step, but let's just go ahead with it. I mean, what we are basically doing is building upon the compilation script that we had written so that it comes in handy. Again, we'll have to do the same thing. We'll have to give it the permissions because it's an executable, and then we can go ahead and run it. Now, if you look at the directory structure, you would see that there is a Sudoku.js folder that has been written that has all of our required thing. So we have a generate witness.js. Again, we have the WebAssembly file, and now we have the witness file as well. Now, what we have done here is that we have everything that we need to tell our Groth protocol to go ahead and generate the necessary things that I can send to my Snark to generate the proof for me. Now, we remember that this protocol requires 2 things. One is the tau, which introduces randomness into my system, and the other part of it is the phase 2, which in our case is something that we are going to use as is from the default, like whatever default circuit would do. So we are not altering it specifically to our application. So let me show you what we are trying to do. So let me go to this file called execute groth16. Now Sudoku is what we are working with. So I've just kept the default circuit name as Sudoku. Now p-tau is like, it comes in various versions. There's version 12, there's version 14. So depending upon what you pass, that p-tau file number has to be referenced. So you have to specifically get that file. There's a location from which you can get it. So depending upon the version you're specifying, 12, 14, you can get that particular file. Now, what that basically, what we want to start with is, when we have compiled it, when we have generated our witness, we want to generate our key file. This key file is the most important file for verification because it has the necessary, you could consider them as seed phrases or the like the randomness that we are generating, so that it's difficult to backpropagate and come back to what was the original things that we started with. So these are standard commands. The inputs to this is your R1CS representation. This p-tau has the file version with whatever version you want, since we are going to be using 14. And this is the output that we are going to get. Right? So we start with generating this key file. Then we use this key file to do the contribution to the phase 2. Now, contribute, setup, these are all standard functions. And the purpose of this is to generate a verification key. Remember, we are not yet at the verification phase. We are still in the phase of generating the necessary inputs for our SNARK to take over and start generating the proof for us that will eventually be used by our smart contracts. So once we have contributed, we will basically be getting our, that is the key that we will be using. Now we can basically export this verification key in a JSON file because we will be using this later. And then comes the important part, which is the aspect of generating our ZK proof. Now, in order to generate our ZK proof, we will be using the final key that we have come up with. Now, what we generated in the phase 1 was the intermediary. What we are getting out of phase 2 is the final key. And we also pass along this witnesses. Why witnesses? Because these are all the signals along with the constraints that prove the satisfiability of our circuit. So this is important. And out of this step, what we are expecting to have is a proof.json and public.json. Proof is what we are going to use in all of our smart contracts. Public.json is again the details of our signals, whatever information was public. And then this is the important part. This is where we are going to verify the proof, right? In terms of verification, what we need to say is that given this verification key, does this proof hold given these public constraints, right? That's all we want to do. Now, another thing is we are not simply building a command line program. We want to do this verification from some sort of smart contract because since we are building a DApp, there will be certain conditions under which a transaction will be called, some operations will be happening. So in order to do that, we will be basically, let's assume that we will be having a smart contract through which we will be calling this proof so that we can fetch this proof and then we can use this proof to take certain actions. Now let's assume that proof is called Sudoku verifier.solve. You can give it any damn name you want. This is the version of Solidity that we have specified that we are going to use. Whatever version we specify here is what we are going to eventually use. We'll come to how to design the contract, what goes in this contract, and what all of these things are doing. And this is the part where all the verification parameters are going to generate it, which are these are eventually going to become part of our call data. That is going to be part of my transaction as well. And none of this is public info, like none of this is private information which cannot be revealed. So we can very well pass it along in our transaction. Now let's understand what this is going to give as an output, whether each of these steps are executing correctly for us or not. So let's like recreate this file and go ahead with execution. Okay, we'll do the drill. Let's just give the permissions and so if you don't have the file, basically it will download the file for you. So you don't need to like manually get it. So what happened is that it just did the steps of compiling, generating witnesses again. So it was an override. This is the aspect of generating the key file. And this is the part of the export of my verification key, which I'm going to use. And this is where I've printed the parameters of call. Now we'll see how these parameters are used and where. Right now it's a lot of hexadecimal values, which actually don't make sense. But what we have done till now is we have built circuits, right? We haven't tested them. We have verified that they work, but let's just also see if the tests work correctly, right? So right now we are in the circuits directory. Like let's go a directory back. So Sudoku has all of our circuits. So what we're going to basically do is we're going to add certain tests as part of it, and we're going to see if the tests work out fine. Now, as a best practice, it's good to like separate out your tests in a test folder. So similar to that, just you can write a test file, and basically what we want to do is that our witness should be able to go from unsolved to solve successfully, right? Given like the equation should be satisfied. Here there are a lot of constraints because it's a 9x9 grid and not a simple multiplication. That's why you will have like essentially whatever is your input, whatever is your output, you want to assert whether you're able to go to that using the witness JSON that was generated. And as part of the tester, I mean, you don't have to write your test cases from scratch. There is a library called circom tester, which is available. So if you look at my, let me go to my package.json, you'll see that there's a circom tester dependency. So it comes along with circom. I've just added it using yarn. So what I'm essentially doing here is I have one of the test case that it should generate the witness successfully given this unsolved Sudoku, and this is a solved, because I already have my witnesses. So I want to make sure that what I have versus what it generates from the circuit, that should match. Another thing is that it should fail because a number is out of bounds, right? I cannot have number 10. Like here, if the solved Sudoku has number 10, this should actually be considered wrong. Like these are basic test cases to do a sanity check. And also we have to make sure that whatever unsolved we have should be the initial state of solved. So, right? Like whatever elements that we have here should at least match here. They shouldn't be different. That's another thing. So just basic checks and practices that we have. So let's just go ahead and execute these test cases. Now, how many of you here have worked with smart contract testing? Can I probably get a raise of hands or maybe a yes in the chat, so that I'm aware how much to go in depth when talking about smart contract and testing in general. Okay, we have one who's done the testing. So it's very similar to that. Or you've also tested wasn't contract. That's great. So, I mean, essentially it's a bunch of assert conditions similar to how you have JavaScript you are basically checking whether the expected output is coming in or not. Also, we shouldn't have repeated numbers in a column or in a row. Right now I have a test case for column. You can add a similar one for a row. There shouldn't be a repeated number in a square. Bunch of this. So what I'm going to do now is just execute these test cases, and all of these four should succeed. If any one of them fails, that means somewhere my circuit is not correct, right? Now, in order for you to do the testing, you have to do a bunch of things. You need to make sure that your yarn has circum tester as an added library. You can use yarn test or npm test instead of Mocha test to do this. So what we can basically do is that we can specify that I'm going to use Mocha as my test script. So sorry. If you don't specify this, basically you'll have to use yarn test and whatever test script that you want to run in general. So this is all that you need to do. Instead of being very specific to the package you want, you can use your package manager to run all your tests. So let me shift the tab which has all the tests. Okay, let me go to the directory. Okay, so let's run all of our tests here. So whatever we were expecting, it was able to generate. The first, what is very important is that it should be able to generate the witness successfully. If that fails, none of this is going to succeed ever. So once your first test succeeds, these 5 should definitely succeed. Okay, so one thing is off our head, that we are not basically, our circuit is correct. Also, you can also enable the logs to see if any of the test is failing. So you would be able to look at why is it failing. What we have done so far is we have built an engine which is going to give me a proof that I have completed the Sudoku. I don't reveal the Sudoku. I'm only revealing the witnesses. Using those witnesses, I'm generating a public JSON which has all of the satisfiable values for which it holds true, but not the exact solution of how I came to this. So what I need to do now is build certain smart contracts. What those smart contracts are going to do is I'll show you what we are building, what our end goal is going to look like. So this is what we are going to build, right? Let me go to the home page. So I want to solve ZK Sudoku games. I don't want to reveal the solution. I go ahead and play the Sudoku and it loads a random game for me. And I basically solve it and verify it via the UI. And I'm not submitting my solution anywhere. This is what I can see. It's not getting submitted. It's just getting verified. And if anybody was not clear on how Sudoku works, you can read it here. So let's go ahead and see how we can reach here. So you do see that after I hit the verify button, there will be a bunch of transactions that need to happen. So for that, we need certain smart contracts in place. And in order to do that, let's go ahead with setting up our smart contracts. So for smart contracts, I am using Hardhat. I know many of you would be used to using Truffle, but given that Truffle is no longer in active development, Hardhat would be a good choice to go ahead with. All right. So essentially, what I'm going to do is I'm going to create another directory, which is called contracts. Going to initialize a Hardhat project. Let me just show you how that's done. Anybody here who's seeing this for the first time, setting up of contracts or how Hardhat works? Okay, I'm assuming all of you are aware of how this is done. So I'll skip that part. So let's assume that I initialized a project. Let me still show you for the sake of it, of how it's done. So what I'm going to, okay, I did a small typo. All right. Cool. What I'm going to do is initialize an empty yarn project so that I have a package manager file. What I'm going to do is now I need hard hat. So let me just add hard hat to it. And what I'm going to do now is basically create a sample project. Like it's best to always start with a sample hard hex project. Okay. So for those of you who don't know, I'll show you how to do it. So why hard hat is preferable is because, you like similar to how we do our testing of code in our Web2 side of things, we basically compile it, run it, check if it works. If it doesn't, we go ahead and make changes. But with smart contracts, if you always go and deploy it on testnet, you will need a lot of test tokens all the time when you deploy it, and that can be costly. So hard hat basically gives you a local environment where you can deploy your smart contracts in a local network, and you can keep testing it. And once you see that your contract is working correctly, you can go ahead and deploy it on the choice of your network from hard hat. So I'll show you where and how you have to define for your like for all of the networks that you want. So you can basically do everything through you can either use command line, or you can also use any IDE through, like you can use either Remix, or you can also use VS Code and have hard hat plugins there, so that you can do everything from one ID. But you can very well do it from here. Now, what I have done here is that I've initialized a hard hat project with all of these, did I? I've just added the dependency. So now I have all the necessary dependencies which hard hat needs. So what I'm going to do is initialize a hard hat project. Now this will be a basic hard hat project. And I'll basically create a sample project. So I'm going to go ahead with the JavaScript project. This is going to be my root. Okay, let's add a git ignore. Okay, let's also have the dependencies with yarn. So let's just do whatever default contract that this project comes with. So what we want to do is we want to basically locally compile our contracts. We want to be able to test our contracts. We want to run our contracts. We also want to deploy our contracts. So these are the 4 more important things that we want to do. So once this is done, we'll go ahead and compile the test contracts that we have. And then we will also go ahead and run the basic tests that this comes up with. This might take like a minute or so. So in the meantime, if you want to ask anything, please feel free to put it in the chat. Okay, we are done now. So what we want to do is we want to compile. Syntax is very, very simple. All we need to do is, so basically compile will compile all my smart contracts. Let me also show you the directory structure before we do that. Okay, so inside my contracts, you will see that there's a very basic contract that you will find on even the Remix ID. So it's basically just building a lock on the withdrawal function, something like that. There's a time beyond which you cannot do it. So assuming it's some contract which does something, now I want to basically compile it so that I can check if there are any issues in the syntax or if there's anything wrong with it. okay, it was able to compile it. Now, what I also want to show you that every default hard hat project comes with certain test files. So these are nothing but, again, certain assert functions. So it should set the right log time. It should set the right owner. Depending upon what your use case is, you can actually change these test cases. And that's why these are good resources to start with in terms of syntax. So describe, if you see that every time there's a block of describe, that means that it's going to run every time. Like, I'll show you what happens when I run the testing. So I'm going to ask hard hat to run the test. So what I've done is that each describe block that I had was defined for deployment. There is validations. Like for deployment and withdrawals, I had 2 blocks. Within withdrawals, I had validations, events, and transfers. So like these are like validation checks that we put in our code or unit tests that we are used to writing. This is what we've done here. And this is exactly what we had done for our circuits as well. Now, what this ensures is that our smart contracts are like we are able to do and compile our smart contracts very easily. Now, if you remember when we were dealing with our circuits, right? Let me go back to this execute growth file. So sorry. We had done a solidity verifier generator. Let me go back to the documentation for a minute and show you why we did this. So I mentioned that this is a trusted system, which means that my verifier and prover are not interacting. So in this case, if I am the prover, I need some verifier. So I need to generate a solidity verifier, which will allow verifying of the proofs on my choice of blockchain. We will be doing all of this on Ethereum. So what I've done is I've generated a verifier contract from my Circom circuit itself. And whatever came out of this is going to act as my verifier. All right. Basically, this gives you 2 contracts. We are not interested in what pairing does. So for now, let's focus on verifier. And we'll also not be looking at what happens here, but we'll be focusing on why and where does it come from. So for that, let me just show you a very simple image here. So if you look at it, there, like if you have any deployed contracts, there will be internal, external calls, right? If you come to this part, right, there is a verify Sudoku, you could call it instance. Now, what that is going to do is there's a function basically. The job of that function is to return true only if the proof and the inputs are valid. And who's going to do that validity check is the verifier function. We are calling it Sudoku verifier.sol. Now, inside that, there is this function, which is going to call the verify proof function. Since we are starting with a 9x9 grid, we also need to make sure that we first verify the Sudoku board. Then we use the witnesses that were generated on top of it, along with the verification key to go and verify the proof. And every time on my UI, right, let me go to my, sorry. Like if you see this generate Sudoku board function, this function is called every time I'm going to go on home and say play Sudoku, it's going to generate a random board for me. So that's the job of that. So these are the things that we are dealing with. So this verify proof is an interface which is there within the contract. Let me show you how that looks like. Now, we generated this. We also generated some call parameters. So those all will come in handy now. Let me open the, yep. So it's a pretty big contract with a bunch of constants that have been defined. I mean, these are defined in the way, like these are constants which are defined according to the proof that was generated. So a lot of it wouldn't make sense and has a lot of mathematics that goes back to it. So we'll not delve deep into it. Like these are all the arithmetic operations that will be done so that the verification process can happen correctly. So let's for now assume that this works correctly and the verifier is also correct. So the first thing for me to do would be to pick this up, Sudoku verifier, and put it in my contracts as well. So what I've done is I've added this Sudoku verifier under my contracts because this is my verifier. I'll write another contract called Sudoku, which will be my prover. The only thing that I've changed here is that since this, like I wanted it to be called Sudoku verifier, I've just changed the name of the contract. And if you remember, here we had specified the version as 0.8.4. So in my verifier contract also, the Solidity version has to be updated to 0.8.4. So yeah, this is what we have to make the change as. Now, the next thing that we need to do is we need to write our prover contract, or the contract which is going to send calls to this verifier contract, right? So let's go ahead and see what we want to do. So we are basically writing an interface for the verifier so that it can basically take all of our signals, which generally is A into B plus C is giving some output. That is what generally it looks like. So this is the standard, you would say, structure that you would follow. Now coming to the Sudoku contract, we again have a bunch of Sudoku board lists that you can put. I've started with 3. You can basically use a random number generator to go ahead with. Like this is a really simple one because you just have one number empty and it gets more complex. So there are a bunch of things that I want to do. I want to have a verify proof function, which is going to call the verify proof function from my verifier contract. I also have a verify Sudoku board function. This is something which follows on the template of how Sudoku works in general, similar to the dynamic programming problem we had seen while designing our circuit. And then in terms of verify Sudoku, this is basically using our witnesses that we generated along with whatever proof that was generated for it. Like all of these things are going to be tallied. You could think of it as prover is giving certain documents and verifier has to say that, okay, what you gave versus what we have is matching, looks good, it's all good. If there's any change that happens in what you are submitting, right? Like if you change anything here from what is expected, your filed proof will actually fail, because for a given Sudoku, there can only be one solution. Hence, the proof what will be generated by the verifier versus what you give has to match. So this is where we start with. We start by generating our Sudoku board. Second thing we do is verify the Sudoku board, and then we call the verification on the solution so that we can check if the proof generated is actually fine. Now, let's say I was smart enough to write the proof that I had. What I also need to do is I need to make sure that all of my contracts are working correctly, right? I never compiled this contract and I never added all of the dependencies of ZK proof in my contracts folder, right? Right now, it's a basic hard hat project with nothing. So if you look at, let me show you the basic structure of what will happen. So when you have a basic project, your hard hat config will only have the Solidity version. And according to the Solidity version, the compiler version will also be added. What we also want here is to have the right, we want contracts to have the SnarkJS library as well, because we are generating a proof as part of our prover contract, which is sudoku.sol. So I'm going to ask it to add SnarkJS as part of the dependency. Then an important aspect here is that across your project, right, we have circuits, we have contracts, and then we have our root of the project. Everywhere your version of Snark.js should be same. Like if you have different versions or if you have updated it at a particular local level, you might see certain errors popping up when you are doing the compiling. So like a quick way for you to check is just check the Snark version here. So Snark version here is 0.7.2, and the same thing you'll also have to do at the root level. Not here actually, like not in your project directory. Maybe you could open another tab. So locally you should check here that it's correct. Like this is what you should use. Just give me 1 minute to close this tab. Okay, and another thing that you should definitely check is that in your project root also we have a yarn package file, which is managing all of our I would say all the dependencies that we have. So you should make sure that that file also has the same version. And let's quickly also check that. So that version is also 0.7.2. Now, what we have done now is that we've connected our circuits with our contracts. At least we've established the connectivity at a theoretical level. Now our job is to make sure that our contracts are working correctly. So in order to do that, what we'll have to do is, if you look at it, in the circuits directory, we had generated two things. We had generated a assembly, and we had also generated another key, right? So we need this key for our verification, and we also need this assembly code that was generated for generating the witnesses from the prover side, and then using that to generate the proof. So every time a new Sudoku board will be generated, a new proof will have to be generated. So we need these two elements to be available as part of my contracts folder as well. So in order to do that, what I've done is, as a structure, I've added another folder called ZK proof. Now in that, I've added these two files. So these are a bunch of numbers which pretty much won't make sense, and these two, right? Now, let's see what to do. I said that I wanted to test my contracts. So like testing smart contracts was pretty simple before, but now what we have to do is we have to verify that the proofs that are getting generated from my contract are actually being verified correctly. That is what I want to test as part of my smart contracts. So I'm going to go to the test file and I'm going to write a test.js. Now, first thing that I need is my Sudoku contract. Another thing that I need is my Sudoku verifier contract. And I've added Chai is basically which I'm using for my testing. Hard hat is what I require for doing all of these things. And I've used the utils of Groth 16 so that I'm able to call the functions of the verifier contract and anything extra that I need. So the first thing that I'm going to do is, like for the testing, I'm going to only deploy them locally. So if you look at this particular function in line 11, this is going to deploy my contracts locally. So the first thing I'm doing is deploying my verifier and the prover contracts that I need. Then I want to make sure that my contract, the Sudoku contract, is able to generate a board. So this function from my board should be generated. Then all I'm checking is that it's a 9x9 board. So I'm just checking the length of the array, as simple as it gets. Then I want to make sure that the proof that I'm generating on chain should be correct. Now, how do we go about it? We basically take an unsolved and solved pair. Very simple, only one number is changing. And what I want to do is I'm going to use my wasm and the key file. I'm going to call the verify proof function. And using this verify proof function, I'm going to check whether the result that was generated was true or not. Like I'm basically checking if whatever input I provided versus whatever proof I got out of this, right, is this correct or not? Now, what actually happens is that my input is this pair, right? And my output is whatever is basically coming solved, like whatever's the solved Sudoku. So A, B, C is the parameters that we need. And I'm going to use the same equation. Obviously, the equation that we saw there was very abstracted and very simple. But if you go and read about how Snark.js works, this is what it is as a grassroots level. There is more complexity added in terms of constraints, but what we are looking for is that what we get here out of the proof versus what we generated from the provider, that should exactly be the same. And another thing is that if I have an invalid proof, that should basically fail. It should not return true. So like I started from here. This was my another input, and this was another input. So what we are looking at is A into B plus C, that kind of argument. And I've kept everything as 0. So essentially, this will actually fail because 0 for us means empty, and that wouldn't make sense in this case. So this should return false. It should also be able to verify Sudoku, which means that principle-wise, this Sudoku should be correct. I mean, I shouldn't have 1 repeating anywhere in the row column or this 3x3 grid. Okay, so how do we go about running these tests? It's actually pretty simple. All we need to do is instead of just running the test, it's also better to write a few utils, which makes the job easier for you to generate multiple of them. Let's go ahead and see what we've done in the utils file. Basically, I mentioned that when we ran our Groth 16, there was a big key that was generated. And I mentioned that whenever we are basically going to call the verifier contract, we would also need to send the call data, right? Which will be used on the fly for the verification part. So in order for you to basically do this entire thing manually every time, you can actually write a util. So I've written a function which will export this call data. And what it's essentially doing is, let me go. So what you're actually doing is calling the solidity verifier function, getting the, I would say, the key as well as the witness and bunch of other things that we generated as part of our execute Groth thing. So all of this, it is basically doing it for you. That's essentially what we did. I mean, if you're working on a project for the first time, you might not do it because it's not intuitive. But given that you now have a project to start with, you can actually use it. So if you look at it, all it's taking from you is the input, which was an amalgamation of our solved, unsolved, and this is the path of our WASM file, which is the WebAssembly code, and this is our key file, which was generated. And this is going to generate the call data for you, which is something that you're going to send along with your public signals. Now that we have everything in place, what we also need to have is a gas reporter. It's good to have it. I'll also show you how to add it, but let me show you how my hardhat file looks like right now. Just give me 1 minute. Yeah. So when you basically add the gas reporter, you will have this optimizer basically added. And you'll also have this. Firstly, you'll have this now available because you'll have to add it to your hardhat file because you will now have it available in your package JSON, like it's imported. You go ahead and make sure that it's available in this context. The next thing we also want is optimizer. Because we seldom take care of doing the optimization when we are building contracts. So let's just go ahead and run the test. So just a minute. Okay. Similar to how we had ran the tests on the first version of our project, we'll also run tests here. So we are able to generate a board. We are able to do all the things that we discussed. And we also get a lot of details if you have enabled the optimizer. So you'll get details on how much time it took for each of the step. So this is basically the runs that it took for it to verify and come to a consensus that everything is correct. Now, by this time, we know that our contracts are able to interact with our ZK proofs, right? But our contracts are still not functional in terms of an application, right? They are, I mean, I'm not able to call my contracts from an external source. I don't know which function to call when. So I need a JavaScript client that will be able to interact with my smart contract. So what I'm going to do is I'm going to write a run file that will be able to handle all of the runtime calls. So generally, how I structure my project is, since contracts are in contracts, tests are in tests, you can write various scripts. So I have a deploy script, I have a run script. You can ignore this shell file. That's not important. So let's look at the run.js file, what it is doing. So the job of this file is to basically call all of the, I would say the first thing that we want to do is I want to generate a Sudoku board, right? I want my call data to be available. And then I want to be able to verify the proof. And then I want to display the result, whether it's true or false. That's all the things that I want to do. So essentially, it's very simple. I have initialized my contract. So this is the contract that I need so that I am able to call the functions. This is the contract that I need so that I'm able to verify everything that happens on the Sudoku board that I just generated. Now, for the sake of simplicity, I have just put the call data as a blob here. You can also put this in an env file and infer it from there. Like this is the same call data that was generated when we executed our groth 16 protocol with the witness file along with our key file. So this won't change until you change anything in your circuit. The moment you change your circuit, this is going to change. And once we have everything in place, I need to basically call the verify proof function. And whatever result I get is something that I'm displaying, whether it's true or false, which means that, like, if you look at the UI, all I'm doing is basically I am verifying my Sudoku. So depending upon, like right now, it will basically say wrong answer because it's all empty. So I want to basically see if I'm able to run my contract. And one thing that I want to mention here is that for saving overhead, it's good to like have this available as a static thing. But if you feel that your contracts can change on the fly and that you are going to change the verification conditions based on certain dynamic attributes, you should basically generate this in runtime. Like similar to how we had generated it in utils.js, you should basically follow a similar approach. All right, let's go ahead and run our scripts and see what is.
Hello?
Yeah.
Eh?
Sorry.
Aina?
I'm sorry if.
No, I mean, I think it was just.
Yeah, Aryan is on unmute, so
Okay,
Yeah.
probably.
that's all right. Okay, so what I am basically going to do here is that I want to verify that everything is running correctly, and if I'm able to like come up with the right solution, I should basically get a correct answer. That's all I want to do. So simply for running the script, I need to call the run.js script. So hard hat is by far the most convenient thing that has happened in the, like, it's too simple to use. It's very convenient. So always prefer to run things in local before you actually deploy and start testing it on chain. So this deployment was done again locally. If I specify a network here, then the deployment will happen on my choice of network. And if you see here true, that means that the proof that was generated for it was actually correct. And I wanted to make sure that my contracts are going to run perfectly well. Now comes the main job. Now, let's say that my contracts are in place, my clients are in place. Can anybody tell me what is the process that I'm going to follow from here? Like, what is the process forward from here? Like, what will I do? What's the next steps going to look like? That has nothing to do with ZK. Anybody? You can also type if you're...
It's a build the front end.
I'm sorry, can you come again?
Will that be to build the front end to consume this, like the data? Or we'll probably need to deploy the smart contract on
Exactly.
the
Exactly. So the first thing is we'll deploy, right? We already have an interaction script in place. So what we'll do is let's just write a deploy script. And I want to do it on an actual network. So it makes sense for me to also add a test network of my choice in my hard hat config. Now, in order for you to deploy on any network of your choice, what we need to do is go to our hard hat config, and inside our module exports, we need to add a network section. You can add as many networks as you want. I've added Sepolia and Mumbai. Mumbai was giving me a hard time with deploying because of the network traffic. So I've actually added Sepolia. And what you also need to do is basically create an env file which has your private key so that the fund transfer can happen. Like, you can essentially, when you want to create a smart contract client which interacts with it, you need to create a signer so that it can execute the transactions on your behalf. So you need to provide your private key and create a signer on like using it. So what I'm going to show you now is the deploy script. Deploy script is pretty simple. I'm sure most of you would have seen it, but what I'm doing is creating an instance of my, just a minute, let me just move it up. Okay, perfect. So the get contract factory is a function of ethers.js, which helps us create like an instance of the contract and deploy it. And I'm going to do it on Sepolia for the demo part of it. You can do it on any network for which you have test tokens. Once I have deployed it, then I can do anything on top of it, because I just need the address at which it is deployed to be able to call it. So in order for me to actually run this, just remember that if you are using process.env anywhere, make sure that that dependency is added, like .env is added as part of your yarn. So .env should be present in your yarn dependency file. So this, make sure that this is present, otherwise your deployment will fail because it won't be able to fetch the, like, this will fail. The get signers aspect won't happen because in your hard hat config, you have this fetching. So make sure those things are taken care of. So let's go ahead and run our, like, let's deploy it. So it's very simple. You want to deploy. We have written a script. If you don't write a script, you can also basically use the standard deploy, but that will basically deploy on like, that will deploy all the contracts, whatever are present. And my choice of network is basically Sepolia. So, wait. Okay, I think I missed a keyword. I didn't ask it to run it, so.
Yeah, should it be run after the hard hat? Oh,
Yeah, it might take a minute or so to do it. And once we have deployed our contract is the end of all the tough things. After this aspect, we want to basically go ahead and build a front end around it. How many of you here have experience of building front end? Maybe a raise of hands. Okay. Now, for the sake of demo, I am doing it on, I'm using a Next.js application. If you want, you can also like do it with React or anything of your choice. Let me just. So we had contracts, we had circuit, and now what we need is basically a front end aspect also. So what we are going to basically start with is we are going to initialize a new Next.js application. And we're going to take it forward from there. Obviously, I'll not delve into details of what should we call it? ZK Sudoku UI. So basically, this will initialize a project for us with, like, let's just go ahead with using, let's say yes to everything. So there are a bunch of things that we still have to do, but I'll show you, like I won't be live coding all of the things, but I'll show you how we go about adding the different components so that you're aware of how to go from like just smart contracts to your front end. So if you see here, sorry, you'll see like a basic project being initialized. So let's just run this project and look at the basic functionality. So it's just the basic Next.js project that we have. Now we'll start adding the components one by one. So the first thing we need is we need ethers.js for all of our interactions. We also need Wagmi for, it's easier for some of the functions. Generally, ethers works for most of the things, but Wagmi comes in handy. And then we need things like, we need Snark.js. We need, we'll see what we need after this. So let's just add all of the dependencies that we have. We have Wagmi, we have ethers, and we have Snark.js also. Okay. And also here we'll have to make sure that the version should be same. So we'll just check the package.json file here once it has added to make sure that the version is 0.7.2. Like version conflicts do create some problems. And we'll also have to import our Snark.js on the client side. So one way is that we copy it inside the public folder, like we pick it up from our node modules and get it into our public folder, or we can basically import it in one of our layout files. Okay, let's just quickly verify our package that the version is correct. Okay, that checks out well. So in order to basically make sure that we have it on the client side as well, I'm going to pick up the file from the node modules wherever the build had happened. And then I'm going to just put it in the public folder here so that it's available for my client. Now, let's just also install it on the client side. And now what we'll have to do is that in our config, we'll also have to make sure that Snark.js can be used. So let me go to the front-end project and show you a bunch of those things since we are almost at time. Yes, you can use it, but like you would be the one who would be generating the proof, right? So you would need to have it available on the client side as well, unless in your application you need it.
Okay, so it's technically possible. We can keep everything on server side.
I mean, you shouldn't ideally. I mean, maybe if you could give me an example where you would want this.
Yeah, you are correct that this proof generation should be on the client side strictly. Otherwise, it won't remain private. But just to enable easy or say the mobile devices or the front ends are not very efficient ones. In that case, if we keep the proof generation on the server side, can just give better user experience for that point of view. Is it technically possible to keep it on the server side?
Maybe for ID-based solutions, it would make sense where somebody is generating the ID for you basis this data that they already have about you. Maybe like an application for enterprises or government-related application, this would make more sense. But all of the applications that I have seen or interacted with, I haven't seen this till now. Maybe it exists, but it's not like it's not possible.
Oh, yeah. My concern was that practically we should not leave it on the server side. I was just asking technically if it is possible.
I mean, technically you can do that. It's just bunch of
Okay.
libraries that need to be available in that environment for you to be able to do that. But it
Got
makes
it.
you susceptible to attacks if you don't handle the data that will be persisted on the server side, because you'll have to store it somewhere or generate it on the fly in the backend, depending upon your application again. I think it makes more sense if you're talking about ID-based solutions. Maybe check out how Polygon or other ID-based solutions are using it. Maybe it gives you more
Okay.
insight into if
Okay.
server-side ZK applications are existing today. I haven't used one. I've only dealt with client-side ZK applications so far.
Yeah, it makes sense to keep it on client side only. I was just curious. Yeah, thanks.
Okay, got it. All right, we have very little time, so let's just skim through some things. I won't be delving deep into the beautification aspects, but I'll be telling you of what we need to do so that our front end has access to ZK proof. So if you look at it, these are all the things that my project had. It has a next config, it has JSON, it has CSS, and it also has Tailwind because I configured it. Now, what I want to do is I want to make sure that like in our public, we added support for Snark.js. Now, Snark.js also need two important things, which is the WASM file, and it also needs the key file. So what we need to do is basically pick it up and paste it here. So I'll just show you. So I've created a ZK proof folder. No, okay, inside public, sorry. I've just added these two files again so that, these are available for generating the proofs from the client side. Now, another thing is I have to create another file, which whatever utils.js was doing so far, now I'll have to add this script probably somewhere here so that it's able to generate the proof on the fly given these parameters. So it's like whatever we had built as a command line application, we have to move the components to client side and make sure that the sequencing of events is in place. And in this aspect, sometimes if you run into any error, right? Like if you see here, I am importing groth16. Groth16 is going to generate this call data for me. This call data is exactly what I had added as part of my run.js file. If you see here, like I can't store all of this in my client somewhere. So I'd rather generate it on the fly every time. So I have to import groth16. Sometimes you might see issues. So like you will get some resources, so that will have details on what are the alternative paths for you if you run into any issues with adding Snark.js support. And apart from this, another thing that will be important for you is to create let's create another ZK proof folder. Inside this folder, we will create another bunch of files. Let's talk about this one first. The job of this is to basically structure the call data that will be going to the verify function after everything is generated. And then once we are at the proof part, we are through and through with what we are doing here. So we have ZK proof, we have the ability to generate the call data. Now we want to connect this code to our smart contracts also. So in order to do that, we will basically go to pages and we'll have to write bunch of files. I've already written bunch of files. So sudoku.js will be the part where I'll be generating the board, getting the contract to generate the board for me and render it on the UI. So you will be getting this code so that you can understand in detail as to how it's working. So that's what happening here. Index is the landing page. And then we have a bunch of other pages. We also need a bunch of utility files so that they can handle things like addresses, networks, fallback networks. So in order to handle that, what I have done is I've I'm so sorry. I've created another utils. In this utils, ABI files have the ABI of my contract. I only need the contract ABI of my Sudoku so that if I ever need to change it again, I can basically change the way my contract gets deployed. This is the deployed address. Inside networks, I have added all the networks that I would need. Since I'm working with Hard Hat, I've added local host also. And I've added Sepolia and Mumbai. I would always suggest you to use Infura or Alchemy whenever you are testing your applications. Don't rely on RPC URLs because they bound to change, like the source that they are pointing to can change very rapidly. So don't generally use it. You might run into a lot of issues. And then we have another network called switch network. Sorry, JavaScript file called switch network. It's basically when you sometimes when you're switching your chain, right, in your MetaMask, when you're connecting to the application, you do run into certain issues. So it's to handle those and give you proper error handling. So bunch of UX related things. And you can add anything of your choice, rendering wise, components wise. So all in all, once you run that and you run yarn dev, you're going to see something like this. And you can connect your wallet. I've already connected it. You can go and play Sudoku. It will basically generate. So this is a very simple one. Let me just put 9 here. Okay, probably something wrong. Okay, yeah. So I'll say verify Sudoku. It should say wrong answer, and that's exactly what we expected it to do. And I mean, I know that it was a little fast, specifically from the front end side. So it is difficult to grasp a lot from the front end side, but the idea was to make you aware that it's not that difficult to connect your ZK proofs with your smart contracts and then putting it all together to a front end. That was the goal of this particular, I would say, workshop. And if you were to deploy it on Vercel, I would send some details along with the, I would say, I'll send some details along with the material that will be sent to you so that you can deploy it on Vercel. It's pretty simple. All you need to do is basically provide your GitHub repo. And you'll also have some tips and tricks of how to make sure that you don't falter or don't expose something when you're building your ZK proofs. And that was all from my side today. Thank you for being such a, I would say, patient audience and sitting through the entire workshop. If you have any questions now or later, you can reach out to me on my socials. It's Laisha Wadhwa across all socials. You can also reach out through any of the TPG community portals. We will be very happy to answer you and help you get started on your journey.
Yeah, we have a WhatsApp group. I hope all of you are on it. So if you have any questions, you can drop it there. You can also, I'm not sure if Laisha and Sneha are on that group, but on the Telegram for sure, if you drop it in the ZK Month channel, then they'll be able to respond. So feel free to do that. I'm not sure if anyone has any questions now, maybe quickly you can take some, or
Yeah. Hey, I have a question
Yeah, go ahead.
that you in the verification section, you were first verifying the Sudoku is proper or not, and then you were verifying the proof that the proof is proper or not. So isn't that enough to verify the proof because the circuit was already checking if the Sudoku was proper?
No, that was part of my test case where I had written that the Sudoku was proper. Okay, you meant
Okay.
my circuit that I was checking or not. So if you see the verify proof function, that was not checking whether the Sudoku was correct or not.
Okay,
Verify
makes
proof
sense.
was called like that. That client was actually calling the verify proof function from my verifier contract and passing it the right data. By right data, I means the call data, the inputs, and also all of the witnesses that we had generated. Those are
Got
all.
it. Makes sense.
Yeah.
Yeah, thanks. I have another question, a little bit related to this also and of the context also. So, if a proof is generated to avoid the reuse of the generated proof, what kind of context we can add, or how do we add that?
I'm sorry, I didn't get your question. Could you give me an example? Maybe that makes it more clear.
Oh, yeah. Yeah. So, suppose I have solved a Sudoku and submitted the proof. Okay. Uh, so, can we prevent resubmission of the same proof?
So essentially what will happen is if you are solving the same Sudoku, the proof is not going to change, right?
Yeah.
So essentially you can have a deduplicacy check, or you can also have a retry check if somebody is just resubmitting the same thing multiple times. So that's the beauty of it, right? Even if you change one thing in what you're submitting, it's going to reflect in your proof. So if you're going to submit the same thing again and again, the proof is not going to change unless you change something in whatever was your input.
Okay, makes
That's a
sense.
fundamental property that it's going to handle on its own from a deduplicacy check. Which means that let's say if you are generating a proof of like you are using your biometric data to generate some proof, it's not going to change unless someone tampers with your biometric. And that's why if something is changing in your ZK proof, right, you won't be able to authenticate, right? So that's why the system will.
Yeah.
So that's why the proof should always be the same as long as the data points are same. That's why if your biometrics are going to stay the same, your proof should always be the same and be authenticated. Unless you are also changing the randomness in your system. So what will happen is that if your proof is changing a little bit, the verifier will know, because it also has access to the call data and the witnesses to make sure that this was the expected proof. So as long as that,
So say suppose, I'm getting. So now I have one example to tell you, like, suppose a biometric has been used to access something, but I want to avoid the reuse of it. So somebody else will take the proof and prove that, okay, I am Gunjan, and he will also be able to access. So to avoid that, if we try to add some timestamp or something, is that possible? So that
you can definitely do that. So in this case, my circuit was very simple, right? I was not taking into consideration any dynamic values which could change, right? So you can add more things which would change it as per the axis of time. That's very much possible.
Okay, makes sense. Yeah, thank you very much.
Thank you.
I hope there aren't any other questions. If there are, then please drop it on Telegram and I'll redirect it to Laisha or Sneha. I think we can wrap up, no?
Yeah.
Yeah. Thank you so much, Laisha, Sneha. It was a really nice session. You haven't been getting a lot of questions. People are going to look at it later and come back to you, I guess.
Yeah.
Works fine.
Yeah. Cool. Thank you so much for your time.
All right. Thank you so much.
Thank you, guys.